Hello everyone, welcome to a comprehensive overview of vectors. Today, I will go over everything that you need to know about vectors. So first, let's start with what vectors exactly are. So vectors are a quantity with both a magnitude and a direction. So those are the two things that separate vectors from a scalar quantity. Because if it just has a magnitude, then it becomes scalar. But when you add a direction, that's when it becomes a vector. For example, when I am just saying I am traveling 55 miles per hour, right now, this is a scalar quantity. But when I add a direction and say I'm traveling 55 miles per hour north, now I am dealing with a vector, since I've met the two criteria of having a magnitude and a direction. Some examples of scalar quantities would be like mass, work, energy, power, temperature, etc. that only have a magnitude but don't have a direction that accompanies it. So now we're going to go over one of the most important properties of vectors, which is vectors' commutative law for addition. So this commutative law of addition acts exactly like how the law of addition for numbers work. According to this law, the order in which you add does not matter. So vector A plus vector B is equal to vector B plus vector A. Kind of like adding number A and B is equal to adding B and A. When you add two vectors, the result is called a resultant vector. The only difference that's going to be seen here is in the way it looks. So if I am to draw out vector A plus vector B, the result will look something like this. But if I am to do the opposite and do vector B plus vector A, the result will look a bit different on this one. But the resultant vector, which I'm highlighting in yellow here, both have the same length because, again, the order in which you add does not matter. One key thing that you want to keep in mind when you're drawing any diagrams for adding vectors is the tail to the end needs to match. Vectors are always added tail to end to find their sum. So the tail of the vector needs to always be put onto the tip of the vector. So here, when I'm adding, the tip of the vector and the tail of the vector need to connect when you're adding them together. Scalar multiplication is what we're going to cover next. So a vector can be multiplied by a scalar, which is just a number, and the result is just a vector. If the original vector is A, and you're multiplying it by the scalar quantity k, then the resultant vector is magnitude of k times A. When you're multiplying by a scalar quantity, it just shows a change in the magnitude by numerical multiple. But if you have a negative number, it means that the direction is switching. So let's take a look at what I mean by an example. So if you have a vector A looking like this, and you have to draw out 2A. So here you're multiplying the vector A by a scalar quantity of 2, which means that your resultant vector is going to be twice the magnitude of A, resulting in your vector looking like both of these put together, or this. However, if I now put a negative sign in front of A, it results in a switch of direction. So negative A means that I am dealing with this vector right here, which is the same thing, but the sign indicates that you need to flip the vector. If I have negative 2A for my vector quantity, I am just putting vector A twice together and I'm flipping the direction because of the negative sign here. And this gives me the vector quantity negative 2a. The next thing that we need to talk about is vector subtraction. One thing you can do is think about it in terms of addition. So for example, if you have vector A minus vector B, what you can do is think about it as vector A plus the negative of vector B. So if you have two vectors and you need to find A minus B, this becomes very easy because let's say you have vector A here and vector B here, and you need to subtract them. You just need to think about it like addition. So vector A over here, and now you need to think about B with the sign flip. So the direction flips for B. So here it is. Then for your resultant, you need to go from tip to tail, and you need to make sure that you connect your vectors together. And here is your resultant vector, A minus B. You must remember that vector subtraction is not commutative. You must perform a subtraction in the order that is stated. By adding a negative of B, we're allowing the process to follow the tail to end convention that we discussed earlier. So here, the tail of the vector is attached to the tip of vector A. The next thing that we're going to cover is 2D vectors. So each vector that's 2D lies on a plane that can be written as the sum of a horizontal and a vertical vector. Let me show you how. So if you have vector A right here, we can rewrite it in terms of a horizontal component like this, which is going to be vector B, and a vertical component, vector C. So based off of the addition property of vectors that we talked about, vector A is just B and C added together. Now, the way we think about horizontal vector B is we think about it as a scalar multiple of the basis of horizontal vectors, which is I. And C is the vertical component vector, which is J. Therefore, if the length of B is 5 and the length of C is 3, then we can rewrite B as being 5I because it is 5 times the I component. And we can write C as 3 times J. We can think about it like 3 J vectors, which each with a magnitude of 1J. And then we can think about the horizontal component as 5I, each with a component of 1I. And J are unit vectors. So unit vectors means that the magnitude is 1. So since the magnitude is 1, you can show them by a hat or like a caret over the vectors. Therefore, I, since it has a quantity of 1, magnitude of 1, it can be written like this. Another thing that we need to keep in mind that we discussed that vector B plus vector C equals vector A, therefore 5I plus 3J is equal to vector A. And this is another way that we can write down what vector A is. Now that we have discussed 2D vectors, let's talk about 2D vector addition. One thing you can do when you're adding vectors is add their respective components. So, for example, if you have vector A plus vector B, what you can do is you can add the x components and the x components for vector B together. And then you could do the same thing with the y components. So let's see how that turns out in an example. So if you're adding two vectors, so let's start with vector A and give it the dimensions of 3 and 1. That means the horizontal component here is 3 and the vertical component here is 1. And to that, you're adding a vector B, which now has the horizontal component of 3 again, but a vertical component of 2. Now, if you're trying to find the resultant vector, which is going to be shown from the starting point to the tail and the tip, what you can do is you can just add the components together. You can just do 3, 1 plus 3, 2, and you'll realize that the new vector components for your resultant vector are 6, 3. And here's how this works. Because this is traveling 3 units in the I direction and another 3 units in the I direction, making your resultant vector a total of 6 units in the I direction. Then you're traveling 1 unit in the J direction and 2 more units in the J direction, making a total of 3 units in the J direction. And because of this, you can just simply add the X and Y components. The next thing we're going to look at is how to find the magnitude of a vector, which can be computed using the Pythagorean theorem. So let's say we have our components of X, Y. What we can do is we can look at it in terms of a right triangle. I'm going to show this by graphing a vector and labeling it as vector A. As discussed before, there are X and Y components, since this is a 2D vector. This being the X component, and this being the Y component. We can now treat this like a right triangle. If we can recall, the Pythagorean theorem says a squared plus b squared is equal to c squared, or c is equal to the square root of a squared plus b squared. And that's exactly how we find the magnitude. We square the component of the x, square the component of the y, and we take the square root. And that's how we get the magnitude. The next thing that we're going to cover is a direction of a vector, which we can easily denote by the angle theta. In order to find the direction, we can think of the vector as a right triangle. Here we're dealing with vector A, which we can denote as 3i plus 4j, given by the coordinates that were given. Now, thinking about it as a right triangle makes it so much easier to get the answer. Now we're going to go back and use our trigonometry rule of SOHCAHTOA, where tangent is opposite over adjacent. So theta is tangent inverse of the opposite leg, which is 4, over the adjacent, which gives us the answer of 53.1 degrees. So now we're very familiar with the rectangular components of this, which is 3, 4. However, we can rewrite this in terms of cosine and sine as well. Now, how do we write 3, 4 in terms of cosine and sine? We have to, again, think about this as a right triangle. Here, if you see, we have a right triangle going on, and we're going to denote this as r, r being the resultant vector. Now, we know cosine of theta is 3 over r. And remember, this comes from the basic trigonometry principles of SOHCAHTOA, where sine is opposite over hypotenuse, and cosine is adjacent over hypotenuse. Now, when we solve this and multiply both sides by r, we get r cosine theta is equal to 3. We could do the same concept with sine, where we get sine theta is 4 over r, again, opposite over hypotenuse. And then we multiply both sides by r, and we get r sine theta is equal to 4. And now we can replace 3 and 4 with the new coordinates that we came up with, being r cosine theta and r sine theta. We know r is 5 based off of the Pythagorean triplet of 3, 4, and 5, or you can do the Pythagorean theorem, which is actually going to make this 5 cosine 53.1, 5 sine of 53.1. So that means in order to find the magnitude of this vector, you can think about this leg as being r cosine theta and this leg being r sine theta. Thank you so much.